Hi students, in this video we are going to discuss about white box testing. As we have already know, uh, we have two different ways of testing. One is black box testing and the other one is white box testing. So about black box testing we have discussed in our previous videos. In this video we are going to see what is white box testing. White box testing, sometimes called as glass box testing, is a test case design philosophy that uses the control structure described as a part of component level design to derive a test cases. Using white box testing method, you can derive test cases that guarantee that all independent paths within a module have been exercised at least once, exercise all logical decision on their true and false side, executes all loop at their boundaries and within their operational bounds, and exercise internal data structure to ensure their validity. Basic path testing is a white box testing technique. The basis path method enables the test case designer to derive a logical complexity measure of a procedural design and use this measure as a guide for defining a basic set of execution paths. Test cases derived to exercise the basic set are guaranteed to execute every statement in the program at least one time during testing. Before we consider the basis path method, a simple notation for the representation of control flow called flow graph or program graph must be introduced. The flow graph depicts logic control flow. Each structured constructing has a corresponding flow graph model. The notation for logical control flow are now shown in a screen. For the sequence if, while, until, case. Here each circle represents one or more source code statements. To understand the use of flow graph, let us consider the procedural design representation, that is flow chart. A flow chart is used to depict the program control structure. So now we will map the flow chart into the corresponding flow graph. Here each circle represents the flow graph node, represents one or more procedural statement. A sequence of process box and decision diamond can map into a single node. So now we will calculate the number of nodes. So totally here the number of node is 9. The arrows on the flow graph called edges or links represents the flow of control and are analogous to flow chart arrows. An edge must terminate at a node even if the node does not represent any procedural statement. Now we will calculate the number of edges. So totally we have the number of edges is 11. Areas bounded by edges and nodes are called regions. When counting regions, you should include the area outside the graph as a region. So region 1, 2, 3 and the last one is the area outside the graph R4. So totally we have 4 regions. Each node that contains a condition is called predicate node and it is characterized by 2 or more edges emanating from it. So here we have 1, 2, 3. So totally we have 3 predicate nodes. Now an independent path is any path through the program that introduce at least one new set of processing statement or a new condition. When stated in terms of flow graph, an independent path must move along at least one edge that has not been traversed before the path is defined. So here we have 4 different paths, like the path from 1 to 11 or the path is from 1, 2, 3, 4, 5, 10, 11. The other path is 1, 2, 3, 6, 8, 9, 10, 1, 11. Similarly, we have another path is 1, 2, 3, 6, 7, 9, 10, 11. These are all the independent paths. That is, if you can design test to force execution of this path, every statement in the program will have been guaranteed to be executed at least one time, and every conditions will have been executed on its true and false side. How do you know how many paths to look for? So, this can be computed using cyclomatic complexity. Then what is cyclomatic complexity? Cyclomatic complexity is a software metric that provides a quantitative measure of the logical complexity of a program. When used in the context of basis path testing method, the value computed for cyclomatic complexity defines the number of independent paths in the basis set of a program and provides you with an upper bound for the number of tests that must be conducted to ensure that all statements have been executed at least once. Now, how to calculate the cyclomatic complexity? Cyclomatic complexity has a foundations in graph theory and provides you with extremely useful software metric. It can be computed in one of three ways. Either the number of regions of the flow graph correspond to the cyclomatic complexity, or cyclomatic complexity for a flow graph is defined V of g is equal to E minus n plus 2, where E is the number of flow graph edges and n is the number of flow graph nodes. Or the cyclomatic complexity is also defined as V of g is equal to P plus n, where P is the number of predicate node contained in the flow graph. So, we have already calculated the number of edges, nodes and predicates. Using this, we can calculate the cyclomatic complexity. So, here it is showing that we can have 4 independent paths. Now, the value for V of g is very important. Why? Because it gives the upper bound for the number of independent paths that form the basis set, and by implication an upper bound on the number of tests that must be designed and executed to guarantee coverage of all program statements. Next step is we need to derive the test cases. The basis path testing method can be applied to a procedural design or to source code. The procedure average depicted is shown in figure. It will be used as an example to illustrate each step in the test case design method. Note that average, although an extremely simple algorithm, contains compound conditions and loops. The following statement can be applied to derive the basis set. Using the design or code as a foundation, draw a corresponding flow graph. A flow graph is created using the symbol and construction rules. Now, we will see the corresponding flow graph for these PDL statements. Next one is determine the cyclomatic complexity of the resultant flow graph. The cyclomatic complexity is determined by applying the algorithm which we described earlier. It should be noted that V of g can be determined without developing a flow graph by counting all conditional statements in the PDL and adding 1. So, determining a basis set of linearly independent paths. Now, based on the V of g, we need to find the linearly independent path through the program control structure. In this case of procedure average, we expect to specify 6 paths. The ellipse ... following path 4, 5, 6 indicates that any path through the remainder of control structure is acceptable. It is often worthwhile to identify predicate node as an aid in the derivation of test cases. Now, we need to prepare the test cases that will force the execution of each path in the basis set. Data should be chosen so that condition at the predicate nodes are appropriately set as each path is tested. Each test case is executed and compared to expected result. Once all test cases have been completed, the tester can be sure that all the statements in the program have been executed at least once. It is important to note that some independent paths cannot be tested in standalone fashion. So, in that time, the combination of data required to traverse the path. In such case, these paths are tested as part of another path test. Although basis path testing is simple and highly effective, it is not sufficient in itself. In this section, other variational control structure testings are discussed. These broaden testing coverage and improve the quality of white box testing. The different type of control structure testing are condition testing, data flow testing and loop testing. The condition testing is a test case design method that exercises the logical conditions contained in the program module. A simple condition is a Boolean variable or a relational expression, possibly preceded with one not operator. A relational expression takes the form E1 relational operator E2, where E1 and E2 are arithmetic expressions, and the relational operator may be less than, equal to, not equal to, greater than or greater than equal to. A compound conditions is composed of two or more simple conditions, Boolean operators and parentheses. We assume that Boolean operators allowed in a compound conditions include or, and not. A condition without relational expression is referred as Boolean expression. If a condition is incorrect, then at least one component of the condition is incorrect. Therefore, types of error in condition includes Boolean operator errors, Boolean variable errors, Boolean parenthesis error, relational operator errors and arithmetic expression errors. The condition testing method focuses on testing each condition in the program to ensure that it does not contain errors. The next one is data flow testing. The data flow testing method selects test path of a program according to the location of definition and use of variable in the program. To illustrate the data flow testing approach, assume that each statement in a program is assigned a unique statement number and that each function does not modify its parameter or global variable. For a statement with s as its state number, we will have def of s where the statement s is defined and use of s where the statement x is used. If a statement s is an if or loop statement, its def set is empty and its use set is based on the condition of statement s. The definition of variable x at a statement s is said to be live at statement s dash if there exists a path from statement s to statement s dash that contain no other definitions of x. A definition use chain of variable x is of the form x s s dash where s and s dash are statement numbers, x is in def of s and use of s dash. So, one simple data flow testing strategy is to require that every DU chain be covered at least one. We refer to this strategy as DU testing strategy. The next one is loop testing. Loops are the cornerstone for the majority of all the programs implemented in software. Loop testing is a white box testing technique that focuses exclusively on a validity of loop construct. Four different classes of loop can be constructed: simple loop, concatenated loop, nested loop and unstructured loop. So, we have the following set of tests can be applied for each set of loops. For example, if you are applying test cases to the simple loop where n is the maximum number of allowable passes through the loop, then you need to skip the loop entirely or only one pass through the loop or two passes through the loop, m passes through the loop, n minus 1 or n and n1 passes through the loop. If it is nested loop, if we were to extend the test approach for simple loop to nested loop, then the number of possible tests would grow geometrically as the level of nesting increases. This is impractical. So, we can reduce the number of tests by start at the innermost loop, set all other loops to minimum value, conduct simple loop test for the innermost loop while holding the outer loops at the minimum iteration parameter value, add other tests for out of range or excluded values. Work outward, conducting tests for the next loop but keeping all other out loops at minimum value and all other nested loop to typical values. Continue until all loops have been tested. In concatenated loops can be tested using the approach defined for simple loops if each of the loop is independent of the other. However, if two loops are concatenated and the loop counter for loop 1 is used as initial value for loop 2, then the loops are not independent. When the loops are not independent, the approach applied to nested loop is recommended. In unstructured loop, whenever possible, this class of loop should be redesigned to reflect the use of structured programming construct. So, we have seen what are all the possible way of testing the white box testing. Thank you.